All right. So hello, everyone. Sorry for the little delay. I was in a meeting. I couldn't get free earlier. OK, so let's see. Last time, we made a lot of progresses. So it was the first week of introduction. This is going to be the second week of introduction. And we are going to build up basically on what we did in the previous lectures and enrich our panorama. And basically build up all the instruments that we will need to describe our universe. Namely, the other time we investigated the space-time in a flat geometry, which is something that we are not going to have in the application of our universe, okay? Because the geometry of our universe is Euclidean, or looks like from the data, but we need to use general relativity because, for example, the metric is evolving as a function of time as the universe is expanding, okay? Therefore, we will need general relativity for that. To prepare for this very important step, we investigated, yes, the space-time, so we have seen the Minkowski space-time. Then we look at how particles move in a space-time, and we describe the basic properties of particles in terms of the momentum, for instance. So this energy momentum, which now is our unique entity, mathematical entity, physical entity. And we investigated also photons. And we realized the fact that photons, just by simple consideration in special relativity, they must be massless as their energy momentum tensor, sorry, it's their energy momentum as the first and the second component identical in rest frame, okay? So, I mean, if we under a proper coordinate transformation of the spatial coordinates. What does it mean? They are a null vector, right? The S is a null vector. Photons are moving along the light cone, okay? And because of that, they must be massless. That's a requirement that is coming from special relativity. Nice. Now, we start to investigate something which is more complicated, because if we want to investigate general relativity, if we want to investigate the effect of gravity, we need to know what is the source of gravity. And what is it? Is it one single particle? Of course not. It's a collection, talking about the universe, is a collection of many particles, right? And then we can represent in terms of a fluid, okay? And for this reason, we will need to expand our concept going from the form momentum to an object which is more complicated. That's the energy momentum tensor. That's the subject of today at the beginning, and then I will start to introduce general relativity in the second hour, okay? So this is the goal now, to go from this situation to this one, where you see, noticeably, we are talking about a rank 2 tensor, we have two indices. Why is that? Because if we have a vector, right, a particle is moving one direction. Therefore, a vector is sufficient to describe a direction. But if we have just two particles, one is going this direction and one in this direction. Oh, we need two directions, two different directions. Say you have a zillions of particles moving in all possible directions. We need to be able to have one object that simultaneously points in all possible directions. Okay? And that's given by that. We are going to see that, okay? So we will enter into the energy momentum tensor after we derive it and define it, and we will start to see why that's the case, why this instrument can do such a thing, okay? Good. So let's start then, and let's start to describe the energy momentum tensor, where it's coming from. Okay, what is its origin? So you know that if we have a system, this you have seen for sure, for real, you can describe in terms of an action, right? Action S, which is just defined as the integral of the Lagrangian with respect to time. But if you want, even more basic, the Lagrangian is the object that describes your system. Maybe a particle, maybe the electromagnetic field, maybe whatever, okay? Good, our system. Then, if we write it like this, you see it's not very relativistic in the sense that we don't have relationship with the 4 interval, right, for the 4-dimensional space. Therefore, what we can do is just by changing, moving from a Lagrangian, especially on the fact that we are talking now for particles, therefore we don't speak about the mass of a particle, but a density, therefore we need quantities that refer to volumes, ensemble properties. What is the density of our fluid, for example, within a certain volume. Therefore, the trick is just by introducing a Lagrangian density. Lagrangian density, and the relationship is simply given by an integral with respect to the volume dV. The t, of course, remains from the previous integral. Okay? Nice. Then what we can do, we have these objects, 3-dimensional coordinates, time. Ooh, nice. Okay, that's a volume in our 4-dimensional space. It's a 4-dimensional volume. Therefore, we can just rewrite it for convenience as this the omega, where the omega is defined as the x0, the x1, the x2, the x3. Mind the fact that the x0 is c dt. Okay? Remember there is a c there if it's not set equal to 1. How a system is going to evolve as a function of time? How is it the system evolving? Well, that's given by the least action principle, which leads us to the Euler-Lagrange equation, the Euler-Lagrange equation. Least action, for which the variation of the action is equal to 0. Okay, so this is the equation, the constraint that defines the path that is following our system, which is the one of minimum length, least action principle. Applying this, so now we can plug in our action into that, and what we get is the solution of the equation of motion. Therefore, we have the Euler-Lagrange equation. The x nu, the L over the Q alpha nu, that's nu, minus the derivative of the Lagrangian with respect to the Q alpha. Where Q alpha are the properties characterizing our system. Okay? If we have a particle, it might be the position. If we have a field, it might be the potential of our field. And that's equal to 0. Okay? That's the Euler-Lagrange equation. The trajectory, if we want, of our particle, or better to say, the equation of motion. Nice. Now that we have that, we can ask ourselves if this system provides quantities that are conserved. For example, a particle which is free, okay, there is no force acting on our particle, as, for example, the energy momentum is conserved. So yes, there is a conservation law. Let's see now for this more abstract quantity. That's abstract because this is just a Lagrangian, whatever it is. Let's ask ourselves if there are conserved quantities. And we know that they do exist, conserved quantities. There is a theorem that tells us that system can have a conserved quantity whenever the variation of the Lagrangian is equal to 0 whenever we perform infinitesimal shift. So meaning, if we have our Lagrangian evaluated at a certain position, let's say x mu, minus the Lagrangian evaluated at a position which is x mu plus some epsilon nu epsilon, x nu. Okay? Some infinitesimal transformation. Well, what's that? Mu, like that. Okay? This would be our variation of the Lagrangian by shifting. You know, take the Lagrangian here, you go in infinitesimal shift along x mu, and then you compute the difference. That's your variation, how much it changes along this sort of four-dimensional shift. Might be time and might be space. Nice. Now what we can do, now that we know that given that we can ask ourselves if this condition lead us to the identification of a variation of a conserved quantity. The answer, you already know, it's yes, because this is the Noether theorem. That basically express this quantity and identifies conserved quantities, whatever we can identify asymmetry in our system. For each symmetry, there is an associated conserved quantity. Now, just before we start with that, little thing about Noether, Emmy Noether. She was a German mathematician, actually. She was not a physicist. And she was called by Einstein and oh God, Hilbert, perfect, thanks, to solve issues with respect to energy conservation in general relativity. The two were playing with general relativity, they struggled, I don't understand. Let's call Emmy, okay? So she came, she got invited, she started to work with her as an assistant or secretary, because at the time she couldn't work officially at the university, and in fact she was teaching in Germany, but she was not a professor. She was teaching, but she was not officially a professor. They also struggled to give her the position. No way. The minister said, no, she's a woman. Come on. We know that the women don't have a mathematical structure in the brain that allow us to deal with certain problems. Okay? This was the assumption. No way, and she didn't get the professorship. Anyway, she solved the problem. And she did more than that, because she helped the two guys to understand energy conservation in general relativity, but she did more. She identified the theorem, so the mathematical proof, that says why there are conserved quantities in physics, in systems. Okay? So she made something completely more general, and this is, I think, the most important theorem that we have in physics. Okay? Noether theorem basically is the key for many, many problems that are solved in physics. Okay? Just as an historical comment about that. Nice. So let's try to work out this action. Let's try to do it briefly. So we have our variation. To identify what is the variation, we can just apply the chain rule of derivatives. Okay? So the variation is given simply by the derivative of our Lagrangian with respect to the alpha variable of our system times the variation of our Q alpha variable system plus the derivative of the Lagrangian with respect to Q alpha nu. So that's the other conjugate, that's the conjugate variable of Q. So that's the derivative with respect to nu of Q. And, of course, Q alpha nu. Okay? The variation of the conjugate variable. Here we are assuming that our system, our Lagrangian, depends on some Q alpha and derivative, let me write it more explicitly, I used nu, Q alpha. Okay? Which I didn't give you this notation, you can also write like that. So whenever there is a comma and a nu, that's the derivative with respect to nu of the quantity. Okay? That's what I wrote here. Just chain rule. So you see, this is a function of two variables, you just apply your rule for derivatives. Nice. Then what we can do? Our system must follow the equation of motion. Therefore, our system must satisfy the Euler-Lagrange equation. And you see that we have the Lagrangian over the Q, the Lagrangian over the Q, which must be equal, you see there is a minus, to that. So these two guys are equal, because we have the 0 there. Therefore, we can get this guy and plug it here. We do that, we obtain the derivative of the x nu, derivative of the Lagrangian with respect to the q alpha nu, derivative of q alpha plus the derivative of the Lagrangian with respect to the derivative of q alpha nu alpha, and then we have the variation with respect to nu of the variation of q alpha. Okay? Nice. Now that we have that, we need to rework out a little bit this expression to try to extract something that is the derivative with respect to nu of something equal to 0. This would be our conserved, the thing which is inside here would be our conserved quantity. So we now try to rewrite this equation such that this expression pops up, such that we can identify our conserved quantity. You see, this quantity is not changing. The derivative is equal to 0. Good. So let's do that. And yep.
Could you please write the index a little bigger?
Bigger? Okay. I will do that. Anyway, you have the notes. You can with the notes you have all the indices. So if you don't see it now, refer to that. I will try to make them bigger. Good. So what we can do now is to realize the fact that this expression, let me do it here, now that we know where we are going, we can sort of apply a property of the derivative, which is the product rule, but backward. So we can realize that this guy is actually the derivative, let's write it bigger than, the derivative with respect to nu of the derivative of the Lagrangian with respect to the derivative of q alpha comma nu of the variation of q alpha. That's easy to convince yourself. Make the derivative of this guy. We have a product here. Therefore, we have the derivative of the first one times the other one untouched plus this guy untouched times the derivative of this guy here. Okay? Nice. So you see that we have this guy equal to that. And we want to arrive at something like that. Okay? That's our goal. So what we do is now we can get this guy and bring it on the other side. Now we have this minus that equal to 0. Oh, we are moving in that direction. That's cute. Then we can realize the fact that q alpha equal to epsilon, that's coming from the transformation of sigma, derivative with respect to sigma, q alpha. And then we can also make explicit what the variation of L is, which is epsilon sigma, the derivative sigma, Lagrangian, which is equal. Now we can arrange, you see here we have a derivative with respect to sigma. This is a dummy variable. We need to extract a nu somehow. That's easy. Because then we can write it as the derivative with respect to nu of epsilon sigma. I can put it inside the derivative because this is a fixed number. And then we have the Kronecker delta, which is a fixed number because it's 1 or 0, right? That we can use to change the label. Voila. Now that we have that, we can plug it here and here. And what we obtain, now we have the nu that we can group because we have, sorry guys, here, the nu and the nu, you see, so I can put it together. The nu of the derivative of the Lagrangian with respect to the derivative of q comma nu alpha, derivative of sigma q alpha, meno the Kronecker delta nu sigma Lagrangian. And then the epsilon, which is a constant, which is fixed for together, I can take it outside our derivative, equal to 0. Done. Okay? So variation, chain rule. Then we have the product rule done the way around. We obtain this one. Then what I do, I can bring this guy and pull it on the other side. Okay? So that we have two quantities equal to 0. And I express this the Q and this variation of Q and variation of lambda in an explicit form. This one and that one. Okay? I use just a Kronecker delta for technical reasons, such that I can have a derivative of all of it with respect to nu. I have a derivative with respect to nu here as well. That is this one here. The other two quantities that I brought on the same side of the equality are this one. This is the thing which is conserved. This is the conserved quantity that we call energy momentum tensor. Indices are nu and sigma. Nu, you see this is on the lower part, which means that it's on the upper part because it's on the lower side of the difference, of the ratio. So that's this nu, and then we have the sigma, which is on the lower part. That's our energy momentum tensor. Okay, you can find it in this way, and you see that there is no metric involved here. This can be used on any manifold. No metric was used, just derivatives. Derivatives and variation, that's it. Okay? Therefore, can be used in a flat geometry or can be used also in general relativity on curved spacetimes. Full validity, any manifold. You don't even need a metric. If we want to make it, also to have it with both indices up, then yes, we need to use the metric to raise the indices. We have seen that, right? And there, if you do that, then you need a metric if you want to change the indices for our T nu mu, which is equal to nu sigma mu, so I'm raising the index, of Q nu sigma. Okay, you see, I have that guy, and I raise the index, I obtain this quantity, which is the L of the Lagrangian of Q alpha comma nu, the derivative, not the variation, derivative of mu Q alpha minus nu, that's our metric, nu mu Lagrangian. That's our energy momentum tensor with the two indices on top. And the conservation law, I just spell it down, is the mu T mu nu equal to 0. So colored, white, white. This quantity, there's no white. Ay, ay, ay. Let's see the leftovers. This quantity can be linked to actually a momentum, right? Because all of that, you see, it's everything referring to density. So the energy momentum and the energy momentum tensor refer to densities. Therefore, what we can do is to perform an integral over volumes. So we get a chunk of our, for example, fluid, okay? A piece of it. And basically, it behaves as a particle, sort of. So it has properties that are also characterizing particles because it's a chunk of material. A particle is a point object. This is a chunk, but it mathematically and physically is described by the same quantity. It can be associated one with each other. So that's, as I said, the energy momentum tensor refers to densities. Therefore, I can define, let's call it P, new quantity, with 1 over C, that I place it just for convenience. There are various notations, so you can find it with the C or without the C, even if C is not equal to 1, okay? So you can find it or not. Depends on how things are defined. And that's the integral with respect to the volume, so that's a three-dimensional integral with respect to space, of T 0 nu. And of course, this is a tensor valid, is a tensor field actually, so it's a quantity valid on all location of the space-time. What's that? That's the momentum. This is the momentum of this chunk of volume of our fluid, for example. The conservation law naturally pops up, because if we take the derivative, the time derivative, right, the 0 of P nu, so of this object, then this is equal to the derivative of this object, of all of that. Derivative of an integral is equal to the integral of a derivative. I can put the derivative inside. Therefore, with 1 over C, integral with respect to the volume of the derivative with respect to time of T 0 nu x. What is this equal to? 0, 0 is repeated. That's equal to 0. Comes from that. Okay? That's equal to 0. This quantity, the momentum is conserved. Now, in doing this derivation, what have I done? I took this guy and I brought on this side. So I had this minus that. Why haven't I done the opposite? I could have taken this one and bring it on the other side. I would have got exactly, I would have obtained exactly the same equation here, because there is a 0. Minus or plus doesn't matter. So it is arbitrary to change the value, the sign of this quantity. So take care about the minuses, okay? This is valid, this is convenient for the signature of the metric plus, minus, minus, minus. If you want to go from this metric to the metric that I used in the other lectures, meaning minus, plus, plus, remember the metric was minus 1, plus 1, plus 1, plus 1, okay? To do this transformation, if we wanted to call it so, you need to multiply this quantity minus 1. Okay? So take care about once you have the nu applied here and you're starting to work with a metric, then you have to take care of the signature. And again, even as a source of confusion, you see that everything depends on L. So sometimes you find L's that are defined with a different minus. Because you see, this equation and this equation are the same. Okay? So it's a matter of notation. The minus is dancing there. You have to know from the very beginning what is the notation that is using through all the computations. One comment about this energy momentum tensor. If we construct it in this way, it's not guaranteed that it's symmetric. Written like this, not symmetric in general. But it's expressed through a matrix, right? And we can diagonalize it. So we can make it symmetric. T mu nu equal to T nu nu. And as well, it's not unique. I'm not going to go into that. You find it in the notes, but it's also not unique. Okay? So let me write it since I mentioned it. Because, for example, you can have an energy momentum tensor. Let's call it T mu nu, I don't know, tilde, just to say that it is another energy momentum tensor. T, use the indices above, T mu nu, can be equal to the T mu nu that we derived like this, for example, plus the derivative of, with respect to the sigma, along the sigma direction, of an object which is done like that, where that's an important quantity, otherwise it doesn't work, and an important property, otherwise it doesn't work. Q nu sigma must be equal to minus, so antisymmetric, with respect of two upper indices. Mu sigma nu. See, I flipped these two. This guy and this guy identically satisfied this representation. Okay, so it's not unique, just to have the full picture. Nice, so this is completely general. As I said, can be applied also on curved manifolds, which is going to be the case for general relativity. Let's now make it a little bit less general. Let's try to identify what is the energy momentum tensor of a fluid. Well, actually, before arriving at that, let's see what's the meaning of it. Okay, T mu nu, okay, what's that? What's T0, 1? What is it? Let's give a look. Meaning of T mu nu. Well, we already know something. I said it here. We already know what is the meaning as its relationship to the energy and to the momentum, because the zeroth quantity of P nu is related to the energy of a system, if we think at our particles, right, at a 4 momentum. The three other components are related to what? To the momentum of our system. And again, to get the example that I'm going to use, if we think about a fluid, okay, it can have an energy density. It contains a mass, mc squared is an energy, and it can be moving. It carries a momentum, okay? Then, again, this is an abstract notation. This can be also associated to, for example, electromagnetic fields. Electromagnetic fields are described in terms of a Lagrangian, and in the energy momentum tensor, we can identify this object, which is going to be the energy density of our electromagnetic field, an electromagnetic field as an energy, and the Poynting vector, right? If you recall electrodynamics, the electromagnetic field is described in terms of an energy momentum tensor like this one, where the 0, 0 component is the energy, you see, nu 0, T 0, 0, energy, and the rest is the energy density flux. Okay, let's give better look into that. So let's write it nicely here. So we have our P nu, which is 1 over C. Then we have the integral over the volume of the 0, 0 component. Nu component. Okay, that's what I wrote there. That's our 4 momentum. Then let's keep in mind particle. What was the 4 momentum of a particle? P nu was equal to what? The energy of a particle over C, and then we had the momentum, which was a gamma in front, sorry, gamma E over C, and then we have the 3-dimensional momentum, where gamma E is the energy of the particle, and gamma P is the energy, is the momentum of the particle. If we write that, then what we can do? Let's see, P0, for example, let's give a look at the 0 component, must be equal to that, equal to E. I'm putting the gamma inside, okay? The gamma is absorbed by this definition E. So this guy is this guy here. Okay? And therefore, our T00, 0, what is it going to be? A density. This is referring to chunk of volumes. Here we are talking about density. Therefore, our T mu nu is an energy density. Let's give a look at the other components. What is PE? Now, for convenience, I just bring the C on the other side. Is an energy density flux over C. Why an energy density flux, right? Well, because, and if I write it this way, our energy momentum tensor is TGE, which is equal to SE. Now I show you why it's in an energy density flux. Density flux. Let's give a look at the units, because I recall you that the momentum E, PE, is equal to EVE over C squared. So we are looking at the unit of measures, okay? Because the unit of measures tells you what an object is. Is a force, is a velocity, is a length, is a time, or whatever, okay? So what are the units of this expression? This we have seen it in relativistic mechanics, okay? There is a relationship between momentum and energy. Okay, what is EV? What are the units? Energy times velocity. This is an energy flux. Yeah. For SE over C squared. Energy times a velocity, meters per second. Okay? Therefore, this quantity is the energy density flux. If you are not convinced by this argument, let's try to enter inside the energy momentum tensor, not by exploiting this expression, but by looking exactly at the component 0, 0. Okay? Now I'm using the -1, such that we have all expressions that are, in agreement with the metric signature that I used in previous lectures. Okay? So there is a -1 in this definition. What is it? If we look at the expression there, we are going to have Q dot. So that's the derivative with respect to time, so the delta 0. The Lagrangian over the Q dot minus L, minus the Lagrangian. Okay? Here I'm dropping the alpha, okay? In the previous expression, I would have alpha, alpha, I just drop it for convenience. What's that? That's the Hamiltonian. Ooh, what is the Hamiltonian telling you? What is the energy of your system? We are talking about densities, right? And therefore, this is the energy density. Nice. Let's give a look at T0E. T0E component. So, how do we start to argue here? Well, we can now, instead of looking at the component, just to change the nu with an E, let's use the conservation law, the one up there. If we want to use the conservation law, we have the nu, T, nu, mu. Here we have symmetry. And I can split the time component with respect to the spatial component. Like that. Yeah?
Just one question. On the right side, in the bracket where you wrote down the unit, well, I can't quite read it. What is it again?
Here? This is an energy density flux. Sorry, then we have a C squared, so we have another velocity. But this guy here, make it clear, is an energy density flux, EV. Energy, joule, sorry. Let's use joule, for example. We're talking about. OK, nice, thanks. OK, now let's start to give a look at the zeroth component. Therefore, we set mu equal to 0, 0, 0, 0. What do we have? The T0, 0 over C dt. C dt is the 0, remember, OK? Here, you don't see the C because you have a dot here. So you have a C that cancels another C, so it drops. Anyway, going back to this, that's this expression. That's the derivative with respect to 0. Now we express the time. plus the E T0E. And that must be equal to 0. What is thing telling you? This is a continuity equation. In general, this is a continuity equation with respect to the muth quantity. That's a continuity equation with respect to 0 component. So you see you have the time variation of T00 must be equal and opposite, so it's compensated with the change of this thing across a surface. I will be more explicit mathematically here. That's the idea, and it makes sense. Imagine, again, our particles. That's easy to picture it. You have your volume. Energy density depends on the number of particles that you have here. Larger the number of particles, larger is the energy. What happens is if they go outside, less particle, the energy goes down. Therefore, the time variation of the energy within this volume is the energy that goes in the flux going outside across a surface. Okay? That's the link between the two. Time variation is given by the fact that we have an energy, in this case energy because it's the 0, component, is going somewhere else across a surface. Okay? Nice. So what we have, T00 over C is equal to epsilon, as we have seen earlier, as we have also seen from here. See, T00 is our epsilon. Therefore, we have the variation, the time derivative of epsilon with respect to time plus C dE T0E must be equal to 0. Okay? I just expressed that as epsilon to make it clear. Now what we do? That's all done with respect to volumes. Let's make an integral. Okay? And we make an integral also by getting this guy and put it on the other side first. So we get this one, and we go on the other side of the equality. So what we have? We have the T epsilon equal to minus, because we went on the other side, and then we have the E T0E. And now we make integral with respect to volume, integral with respect to volume. Now what we can do? Look, what do we have here? Oh, we can use the Gauss theorem. The Gauss theorem tells us that we can link this derivative. Well, this one actually, we leave it like that. We use the Gauss theorem for this side, where this quantity is equal to minus C, that's a constant that we are not touching. And now we have the integral, not with respect to a volume, but with respect to the surface of this volume, which is equal to T0E, let's call it then J, and then the area AJ. So that's the integral over a surface, which is described by this surface element. And, a surface is a vector? Yes, it's a vector. Why? Because it can have an orientation. Okay? And if you want, we can write our dEj as the direction along which we are orienting our surface and the modulus of the surface. So that's the area A, and the surface direction is given by E. I placed the index below just to exploit this, the Einstein notation for the multiplication. Okay? These two things are the same. Then what we have? The integral of a derivative, so that's equal to the derivative of the integral. And here we are. What is that? That's the energy. What is all of this? That's the variation, the time change of the energy. Nice. What is this then? Then this is the variation, so the change, let's call it change. Change due to what? The energy going across a surface. What is then T0J? Is of energy density flux. It goes across a surface. Energy is not created or destroyed, it's going somewhere else. If that's the case, we conclude that Ct0j is equal, as I call it J, I call it S, to stand for our energy density flux. And in fact is joule per meters per second. Let's complete our picture. And we already know, I showed you that this expression is a continuity equation. Therefore, we must have a continuity equation also for the other component of the energy momentum tensor, for the T, E, J components. So now we set mu equal to E, which is 1, 2, and 3. Okay, the 3 special components. Therefore, we do exactly the very same trick. We are going to have T0E over C derivative with respect to time plus the J, T, E, J. Which is equal to what? Look, we have T0E. We know what is it. We derived it earlier. We understood what that thing is. That's our beloved S. So that SE over C squared, there is a C that is coming up here. So from C we go to C squared. With respect to dt is equal to dj dij. I didn't touch the other part. Okay? Nice. But what is this thing here? Let's call it PE. Let's call it PE. And therefore, this is equal to the PE over C squared dt. Let's bring the C squared here. The J Dij. That's equal to 0, our beloved conservation law. What is that? That's like for the particles. That's the momentum. Okay? I wrote it. The expression up here, we have a relationship between momentum and the particle. Yeah, I forgot a 2 here. 2 here. Okay. That's you can recall it from the particle. We have P equal to energy VE over C squared. That's exactly the same expression. And this is our S. That's our energy density flux. Therefore, this guy here is a momentum density flux. That's the momentum, and that's the flux across a surface of this quantity. Therefore, is an energy momentum density flux. T-E-J, we can call it sigma EJ. Sometimes you find it written like that. Is the momentum density, because everything with respect to the energy momentum refers to density, flux. We understood the meaning of all the terms of the energy momentum tensor. As a summary, we have that the components of T mu nu of our energy momentum tensor are the energy density Then we have the energy momentum density with the energy density flux given by x over c. That's component, x. Then we have s component y c and s component z c. We can symmetrize it, therefore we have the very same quantities here. And then we have our sigma. We have our sigma x y, sigma x, sorry, that's x, that's x y, and sigma x z. Here we have sigma x, so that's y y, sigma y z, and then we have sigma z y, sigma that z z. Okay, and we have this diagonal, and then we have this box, which is also, and those elements are equal to this other box. That's our energy momentum tensor. That represents energy, energy density flux, and the momentum density flux. This information here is redundant with respect to this one, and the information here is redundant with respect to these other components. Okay? That's our energy momentum tensor. Let's give a look now at a fluid. What should it be? Well, if we think about a fluid, you know, we have many particles. They can even be photons. Okay? They can also be photons. That's a photon gas. Anyway, whatever. We have particles, and a fluid, if we take a chunk, is described by a collection of numbers. What would they be? They would be the density, they would be the pressure, and then they would be a velocity. If we're talking about a relativistic fluid, then would be the force velocity of this chunk of volume that we are considering. So you see we're looking at ensemble properties. Take a volume containing many, many particles, and a fluid is characterized by these numbers. If our fluid is at rest, we expect that the energy momentum tensor at rest, mu nu, all the component, is actually diagonal. Diagonal, where we have rho c squared, that's the energy density, right? Mass c squared is an energy, rho per c squared is an energy density. And then we have here the pressure, and the pressure. What's that? That's the energy density of the system. That's the pressure going in one direction, the pressure going in another direction, and the pressure in another direction. Why are they the same? Take a fluid. You know that if you take a small element, the pressure of this fluid is the same in all possible directions. Okay? So we expect the energy momentum tensor to obey this rule. Then we can ask ourselves, what is the most general energy momentum tensor that we can have with this quantity, and accounting for the transformation of the energy? Because we have an epsilon, and the epsilon, recall yourself, depends on the transformation of the system that we are using, right? Remember the Lorentz transformation. And it can be easily obtained by just projecting the energy momentum tensor, T mu nu, on a certain direction. So if you are an observer moving with this force velocity, the energy of the energy momentum associated to this system is equal to that. You just have the energy momentum tensor of the system projected on the force vector describing your velocity in the space-time. So, having that, what is the most general representation of the energy momentum tensor we can have? Well, we have that our T mu nu must be equal to some number that we don't know what is it, times u mu u nu, because this transformation must apply. plus what? Well, we are in a space-time, that should be the metric. Therefore, the simplest expression that I have is this one. Just a linear combination of the general transformation of the energy density of a tensor plus a term that might or might not depend on the metric. Okay? G mu nu. We have a G mu nu in our expression. Where did I put it? In our expression there. Okay? Ah, sorry, I'm using G. Let's use nu mu nu, since we are in special relativity. Beautiful. Now we can ask ourselves, what is A and what is B? We need somehow to link it to the property of our system. Therefore, we can look at this expression at rest. At rest, we have that our u mu is equal to what? C, 0, 0, 0. We have seen that again in relativistic mechanics. Therefore, now I use this expression here. What we are going to have, T0, 0 is equal to A U0, U0 plus B G 0, 0. Nu 0, 0. But we know what is U0 and U0. Is C. We know what is nu 0, 0, minus 1. Therefore, that's equal to C squared A plus B. And that's equal to rho. Must be equal to rho. Then, for the other components, let's give a look at T, E, E along the diagonal, because I'm working along the diagonal. You see? That's the constraint I used here. Okay? TEE is going to be equal to 0, because the other components are 0, minus B. And what we get, this must be equal to P. This is this other constraint that I'm using. Therefore, we obtain, so that's equal to P. Therefore, the constraints that obtain are B equal to minus P. And now that we have P, we can plug it here. That tells us that A is equal to rho plus P over C squared. We have the energy momentum tensor components. Because now we just plug it A here, P here, and we have our final expression. That's it. And this expression, yes, satisfied this condition here. You can look at rest, this expression is going to hold up. That's beautiful, also because with that, we have the energy momentum tensor of a fluid, whatever the fluid is. We know that this expression holds. And this quantity gives us hydrodynamics. If we are considering our fluid to be a fluid, these are the hydrodynamic equations. Hydro equations. Let me do it up there. Let's take the nu T mu nu equal to 0. The mu equal to 0 is energy conservation. That's, in this case, what is conserved here, rho. So it's a fluid going across rho. So that's the continuity equation. What is commonly called continuity equation. For mu equal to E, That's referring to the momentum. That's the momentum conservation, which in hydrodynamics, this is just the Euler equation. Is it enough to solve the equations of hydrodynamics, to solve the full system? No, we are missing one equation to close the system of equations, and we need to include. Sorry, that's energy conservation. So that's the conservation of energy. And then we have the continuity equation, because rho is flowing from one, matter is flowing from one location to another. Therefore, we have d mu rho equal to 0 must obey as well, and that's matter conservation. That we need to add on top. So this is this guy here. Here we need to include also matter conservation. The particles are not constructed or destroyed. They're moving from one region to another. And then we also have a relationship. We need also a relationship between pressure and the density. So a function that gives you the pressure, and the function depends on the density, and most in general, also the temperature. Why am I stressing hydrodynamics? We are doing cosmology. Who cares about a fluid? Because our universe, we are going, the matter, for example, the baryons, dark matter, and so on, that are within our universe, we are going to model it with a fluid. Okay? And the hydrodynamic equations tells you how the fluid is behaving. We can have perturbations in our fluid. Do we have it in the universe? Yes. I showed you at the beginning, right? The universe is homogeneous and isotropic on very large scales. But if we go on smaller scales, there are energy density fluctuations. And if we have baryons, they have a pressure that is different than 0. And we are going to see that there are sound waves propagating. And the imprint of these sound waves, we do see in the cosmic microwave background. Okay? We see them in the distribution of galaxies across the universe. Okay? So that's extremely important for what we are going to do. Let's make now a little summary about the topics here. So here I described the momentum, the energy momentum tensor. Well, actually I started here. So we started with the energy momentum tensor. I gave you the key ingredients and the key equations to describe our system, a system that is given by an action based on Lagrangian. So the action is the integral of the Lagrangian with respect to time. I then describe the Lagrangian density with respect to a volume. We use the least action principle to get the Euler-Lagrange equation to have the dynamic of our system. And then we have identify conservation laws using Noether theorem, meaning identifying the symmetries in our Lagrangian density. Doing that, we find out this quantity which is conserved, the energy momentum tensor. Here, now represented with both indices up and having the metering popping up. And this guy obeys this expression, and therefore is our conserved quantity. That's the quantity of our system that is conserved. Then I gave you the link of the 0th component of that tensor with the momentum of a chunk of volume of our system. I gave you generic characterization of the energy momentum tensor in the sense that can be made symmetric, which is a representation is not guaranteed to be symmetric, but we can make it symmetric. And it's not general, so you can also rewrite it in various ways, obtaining the same, for a system that still solves the same energy momentum, the same Euler equation, the equation of motion. Then I gave you the meaning of all the components of our metric tensor. I skip all of that. I go directly to the final result, where we have that the components of our energy momentum tensor, the 0, 0 component refers to the energy density of our system. This is the energy density flux, and this is the momentum density flux of our system. And then we went a little bit more specific, and given this general construction, we build up a model. So this is not coming up from fundamental principle of physics. This is a model. We are getting the things that can represent the system that we are interested in this case, a fluid. And therefore, we construct it. We construct a system that must be characterized by this quantity, density, a pressure term, and a velocity in a four-dimensional space. We know that the energy momentum tensor must transform in this way. Sorry, the energy must transform in this way according to the system of the observer. And the most general fluid that contains this guy here, and the metric, the simplest and most general, is this one, just a linear combination. Okay? Then we identify the constant A and B by making a constraint of this expression with what we expect for our fluid at rest, which is this one. Okay? Then for free, we get all hydrodynamics equation, because this quantity now that is expressed, we know A and B. We have the energy momentum tensor for our fluid fully expressed. And where is it? Here. And then by just exploiting it, by knowing that this is a conserved quantity, we can have all the equations, these 4 equations here, plus matter conservation that must be obeyed by our particles, and an equation of state that link the pressure to the density that characterize the kind of particles that we have, okay? Because the pressure that exerted by our system depends by how the particles are interacting one with each other. Okay, this gives you then the pressure, and with the rest, sorry, how they interact with the rest. This set of equations allows you to quantify the behavior of your system, track its evolution. And that's key when we are going to study the distribution and the evolution of structures within our universe. That's the set of equations that we are going to use. Okay? Plus, this energy momentum tensor is going to be the source of gravity. Recall Newtonian mechanics. What do we have? Nabla square of the potential, of the gravitational potential, is equal to 4 pi g rho. We have a link between the gravity, the gravitational potential, and the source. In general relativity, we are going to find an expression which is very similar, where the density, which is a scalar, therefore it's not an invariant, because it depends on volumes, and a three-dimensional volume is not invariant under Lorentz transformation. We are going to substitute it with a Lorentz invariant quantity, T mu nu. Okay, this obeys Lorentz transformation. And we are going to find a term that depends on the geometry of space-time that links the two. So this guy tells to this guy how it looks like. But look at the energy momentum tensor, depends on the metric. Therefore, this guy affects G, but G enters in the energy momentum tensor. This expression gives you a theory which is non-linear. Electrodynamics is a linear theory. You have a field, you have the equation of motion of your particle, or the way around, you have the source, which are your charges, and that's the field, full stop. You don't have the field that enters here that modify each other, okay? You don't have this loop. In general relativity, you have that. That's why it's complicated to solve those equations. And you can do it analytically only for very simple systems, as our universe. Our universe, we're using the cosmological principle, homogeneity and isotropic, is the simplest metric that we can use in general relativity. Okay, so we are going to have analytical solutions for that equation. So now, at this stage, we can characterize this guy with the next lecture, I'm going to start to characterize this G mu nu term. So this term that describes the perturbation of the space-time. So we're going to substitute a gravitational potential with a perturbation of the metric, okay? Something with a specific metric. Good. So we can stop here for 5 minutes so that I can